Hello again, friends. In this video, we're going to be trying to find the volumes created by rotating regions around the x-axis using integration. And specifically in this problem, we're going to be using the disk method. So what that means is when we kind of break down our region that we're trying to find the volume of, the shape that we have, we're going to be kind of like splitting it into disks. So it's like when you cut a tomato, right, you cut it straight down, you get all these nice little slices of tomatoes, these disks. So that's going to be kind of the basis for the equation that we're going to be using when we integrate. So the equation that we're going to be using is going to be from some range a to b, and we're going to use pi r squared dx. So we see that this is our width, and then this is kind of it's a cylinder shape, right? You're multiplying a width by the area of a circle. So you see that that's kind of gets us our disc. That's like the pieces for the discs. So to kind of illustrate this, we are going to, let's start by graphing what we got. So we're working with this equation right here, and we're working from, I believe it's 1 to 3, and we have a parabola that starts at 2. So if we're to graph this guy, he kind of looks something like this, right? And we're going from 1, 2, 3. So I'm just gonna kind of extend them out a little bit there. So we're working with this region right here, and we're rotating about the x-axis. So that means we're going to be taking our x-axis and spinning it all the way around. So this guy is going to come down here as well, and it's going to be working with the same region underneath here. So this is the region we're trying to find the volume of. Now, since we're rotating, we have to kind of consider what the overall shape of this guy is going to look like. So when we rotate it around, right, if this is our axis, you take this region right here that we have, let's just say that this is what we're working with. So this is 1, starting 1, and this is 3. And we rotate this all the way around. We need a circle, and when we rotate this all the way around, we're going to make our circle. So we see that what we get is this kind of punch bowl shape for our figure here that we're working with, right? So we have to consider now, thinking back to what we've done in the past, right? How we kind of broke these problems down is we looked at a rectangle, right, in here, and we said, hey, it has a width of dx, so cool, we have our width dx. But we're taking this rectangle and we're rotating it all the way around our x-axis too, correct? So when you rotate it all the way around, oh, I'm sorry, I realized I drew this at the wrong spot. We started at x equals 2, right? So this guy's going to be up here. My apologies, friends. That looks a little better. A little lopsided before. So when you rotate, like I was saying before, this disc all the way around, or this rectangle all the way around, once again, we're taking it, and it's inside here, right? He's kind of hanging out in here. And we're rotating him all the way around. So we see that we get this like sliver of a circle inside our punch bowl shape that we got. This like megaphone style shape, right? We rotate we get a circle in there. So we have to figure out what the area of this circle is, right here, and multiply it by the width of what it is, our dx, and that's where this comes from. So we have to figure out, we have our bounds, and we know what our width is. We have to figure out what's our radius of this circle. Well, as we move throughout this shape, right, so here it's this big, as we move throughout, towards the ends here, he's going to get bigger, right, our radius. So we see that our radius is this line right here, is the same as right here. It's defined by our function. Our radius is small at the beginning, bigger at the end. Our function maps out what the radius is going to be. So we can plug in our function for our radius. So knowing that, we can rewrite our integral as from the bounds 1 to 3 of pi. I'm going to pull my pi out just because we're just multiplying, he's just a constant. I'm going to pull him out, pi, and we're going to plug our radius in, which we said was our x squared, our function, plus 2, squared dx. Now that we have our integral written out, we can solve. So this is the same thing as saying pi times 3 or to the bounds 1 to 3 of x to the 4th plus 2x squared plus 4. Once you FOIL everything out, that's what we have. And now integrating, we see that we're going to have a 4x, because we add 1 to our exponent. We're going to have x cubed, and then, oh, this is supposed to be a 4, right? When we FOIL everything out, we're going to have 2 times x squared plus another 2 times x squared is going to get us a 4x squared. So we're going to have 4 over 3 x cubed. We're going to add 1 to our exponent here. We're going to have 1/5 out in front. So that's our completed integrated equation. And our bounds still hang out. We haven't found those yet. So we're still going from 1 to 3. So once we plug in our bounds, well, let's see what we get. We're going to have pi times, we're going to have 1/5 times 3 to the 5th plus 4/3 times 3 to the 3rd plus 4 times 3 minus everything times 1, so we're just going to have 1/5 plus 4/3 plus 4. So plugging this into our beautiful calculator, we see that we get this whole guy becomes a very ugly decimal at 91.06 repeating, which is the same thing as over 5. And then we have to remember we're still timesing pi in. So this is 1,366 over 15 pi, which you can't see that answer, and I didn't realize that, so I'm going to write it up here. We have 1,366 over 15 pi, because this guy is still times by pi out over here. So that is our answer for our volume. And so the way we go about, like I said, is we plug in for the disk method, we can just plug in our radius, which is just the function, and solve from there.